All right, this is lecture, I believe, 8 today, right? Yeah, lecture something. ECGR 41, 61, and then all the other ones in production robotics. So today I'm going to cover systems engineering. How many of you have had senior design 1 already? Even if you're a grad student, all right? So a lot of you. I am not sure if you did my lecture on systems engineering, but the one aspect, in fact, I talked with Tom earlier, and Tom was saying, man, this was tough. I never had to build a circuit that moved, all right? So that's some of the characteristics of a system that is not a stationary thing that you just point and say, look at this. But you're going to get different aspects of a circuit that potentially moves. All right? Oh, in fact, here, let me show some of these. Here, can you bring yours up? Just for grins. Anybody want to bring up theirs? All right, so here's one example of a robot. And what does this have that I probably like?
It's not up there yet.
Is that up there?
There we go.
All right. Somebody change the brightness on this thing again. Yeah, that looks better. So lots of seemingly looking bundles, right? Even though you didn't tie them together, it's not a total rat's nest. And can I turn this over? Does it fall off? All right. Where things are pretty much in bundles, nice little connectors and all. Make sure you return, if these are the ones that you borrowed from us, make sure you return them because we actually can use them. So, think about this. This is a system. A system made up of what?
Microcontroller.
A microcontroller, so a computer aspect with code. What else?
Motors.
Motors, electrical, power, electrical, and? Well, sensors I'll do an electrical, but what's
Battery?
here? Like this.
Chassis.
Chassis, wheels, mechanical aspects of it, right? And so the whole aspect of what I want to talk about today is a system. So our system, what is a system? So this is a presentation that I actually got from NASA when I worked there. Yes, I am a rocket scientist. Did you know that? I'm a bona fide rocket scientist, and I've got the videotape to prove it, which I'll show during the break.
It's a videotape.
Pardon? So today I'm going to talk about just briefly system, and then we're going to do a lot of work identified with let's build up a robotic system. Let's look at all the different pieces. But the other thing I'm going to start looking at is how do you develop a robotic system starting at the beginning. So what's the first thing a robotic system has? Any system has. Requirements. All right, so we'll take a look at how you develop those requirements. So again, a system, integrated composite of, interesting, people, products, and processes. Provide a capability to satisfy a stated need or objective. So again, processes. Think about some of the bigger systems out there. In fact, there's one extremely huge system nearby, right next to a dam.
Power plant?
McGuire Power Plant, which is a nuclear power system. It is the fact that it doesn't have a cooling tower makes it a little bit smaller than a lot of nuclear power plants, but it is still an extremely complex system. Even your typical airplane is a very complex system, and it's easy to see how if some of those components don't work in the system, like the Boeing Dreamliner, right? We've talked about that. So again, personnel, facilities, processes, hardware. If you think about a nuclear power plant, does a nuclear power plant have people?
Yes.
All right, it doesn't consume people. You don't use people as the fuel, but people have to work on the processes. They have to identify, this is how you start up the nuclear reactor, this is how you shut it down, this is how you keep it running, and of course the hardware, the plant itself, as well as the general facilities. But this is, for example, this is very centric on the space program since this was developed by NASA. So, examples of a system. So I went to NASA a couple of times over summer, and you know what that is over there? I mean, other than me,
Hair dryer.
that is the rocket for the shuttle itself, not the additional booster rocket, but it is one of the 3 engines that go on a space shuttle. Now, I like this. I posted that on Facebook or something like that, and one of my students said, "I don't think that engine could get you into space." So I got really sad and I ate another donut. All right. So even look at that. What do you see? There's a lot of stuff on there that's beyond mechanical, right? You see there's a lot of wires, a lot of valves. So even that engine over there is a system itself. And that system is associated with just one small part of the entire space shuttle orbiter. And so that's a picture of a space shuttle that one of my buddies that I worked with took because I wasn't able to be there for the landing. That's at Kennedy Space Center. Oh, in fact, that's at Kennedy Space Center too. I had a neat tour of the Space Center, which I'll show you later. So you think about inside the space shuttle, of course you have that engine and a whole bunch of other subsystems. Avionics, what goes in the payload, etc. And if you think about it, the orbiter itself, the part that lands, is part of a launch vehicle that you add the solid rocket boosters on it, as well as the external fuel tank. And now that's a system of systems. And then if you think about all of the space transportation, so the payload that goes inside the launch pad, there's mission controllers sitting somewhere in some room, making sure that things go correctly, both at Kennedy Space Center and at Houston. So now you're introducing people in this system. And then, of course, a system of systems, you have the entire space transportation system and the International Space Station and the tracking, I forget what TDR or SS, but it's the satellites that actually transmit data from the shuttle and the International Space Station back to Earth and up. So they position satellites that you can get things there at any time. So what am I trying to say? Obviously, a system can be made up of subsystems, which can be made up of subsystems, which can be made up of subsystems. So what does that tell you about a system? When do you get to the end, right?
Do you?
Say that again?
Do you?
Do you? I don't know. But, at one point, you have to break down a problem far enough that you can understand what it is. So, if we look at systems engineering, it is an approach to the design, creation, operation of systems. And a system engineer will be somebody who does this typically, and it's a little bit different in this college, but I'll say that that's unusual. A system engineer is typically somebody who has a degree in one of the major disciplines of a system. Computer engineering, electrical engineering, mechanical engineering. And a systems engineer will be somebody who is more experienced and can understand all the other disciplines combined. And very often a systems engineer is not doing manufacturing, but they're developing an entire system of whatever it is that you identify. So if you look at that video camera right there, that is a system. There is software that's part of it. hardware, both mechanical and electrical. So the approach of system engineering, identification, quantification of system goals, alternative designs, design trades, you're kind of trading off one feature versus the other, and verification that what you're designing is appropriate. Now, the whole idea of system engineering is it's iterative. You don't necessarily say, I have this idea, poof, it comes out of your brain into something that's automatically made or manufactured. Of course, there's going to be a lot of discussion of how you do it. So let's take a mobile phone, which I don't bring anymore because it rings. So, anybody have a mobile phone? So, you think about this system, right? And if you're going to create this system, you're going to have to pull together what sort of engineers and designers. So let's write this down on the board. These are going to be sneaky. I'm going to turn it on when you're not watching. What kind of engineers would work on designing something like this?
Mechanicals for the case.
All right, mechanical for the case. Computer. So computer. For software.
Hardware.
Electrical.
Material.
Material for
Battery. The glass.
Plastic solutions, stuff like that too.
plastics.
Systems.
Say, speak louder.
Systems.
Okay, systems. Which I'll call the glue. Because the system engineer is the one who's responsible for pulling everybody and telling them how to work or helping them work together from a technical standpoint. What other engineers do you think might be involved in electrical technology? All right, so we'll say technicians. So it's everything from electrical engineering technology to mechanical engineering technology.
Software engineering.
Software I'll lump under computer.
Chemicals. The chemical material.
Manufacturing, I was kind of looking for that last one. How many of these does an engineer really build? Typically, at least one or two, right? They have to make sure it works. And then they hand it off to a mechanical engineer, and they do a lot more. Or I'm sorry, manufacturing engineer, and they do a lot more. So from that respect too, there might be another type of engineer. Test engineer, you gotta make sure it works. What was another one up there?
Process engineer.
Process. I'll call it manufacturing, how about that? So, you better make sure I didn't turn that on. Plus it's Android, so I wouldn't know how to do that. So we have now a lot of different engineers involved in a robotic product, all right? So what I would like you to do is, let me see if I comes up with the next one, is to think about a real product. Let's see, what's a good product that is robotic that everybody knows about? A Roomba, very good. All right? So think of all, does everybody know what is inside a Roomba? Oh, I should have brought a whole bunch. All right, let me back up a little bit more. See these little robots you just did? I want you to identify all the different, no, that would be a little bit later. Gosh, how am I going to do this right? Because it's getting to the point where I see lots of people with the food coma because of the donuts, right? So I need to take a break and have you start doing something. Let's see, system, what would be a good system that you could decompose?
The stomach.
Say that again?
My stomach.
No. No, it would be really scary.
The whole system.
A car is a good one.
All right, an automobile. So your assignment is identify We've talked about a space shuttle as a system of a system, right? Identify the subsystems of an auto. And you can make it as complex or as simple as possible. And let's make it really simple. Let's call it a Yugo. You probably don't even know what that is, do you? A Honda Civic. It's a small car. It's not hybrid. We'll just say the regular Honda Civic. So, between you and your lab partner, identify the different subsystems of an automobile. All right?
Are we turning in? What type is
So let's take a look at what you think is going to be in this automotive system at like the first level. So what do we call the first level? The top level. What do you call it though?
Car.
Okay. You want to call it car. Yeah. All right. What about a subsystem? Give me an idea.
Drivetrain.
Drivetrain. I like that. I've heard it several places.
Chassis.
Chassis.
Fuel system.
You still missed out. There's one more S in the middle.
Where?
In the middle.
Really?
It's SSI.
No. Somebody said fuel system. Oh, what the heck? I'll do that. If I could spell fuel system right.
ABS.
Interior.
Here, I'll take interior.
More of a comfort.
ABS brakes.
I like something even bigger than just brakes.
Wheels.
When I see mounts something even bigger than that.
Motors.
Well, we got engine, that's drivetrain, or
Transmission.
the transmission is part of the drivetrain.
Drivetrain, engine, transmission, rear end.
Transmission, or I'm sorry, engine is included in drivetrain, right?
AC. You would have something like suspension to talk about the moving components.
Yeah.
Okay, that's not part of the chassis?
Depends on which way you want to look at it.
Sort of.
I'll put the air conditioner inside the interior. How about this? I'll include electronics, right? In fact, I'll include electrical. That includes the computer, which we'll break out a little bit later. What else?
Materials for the battery.
All right, I'm talking, remember, first level. Really, really high level.
Needs a battery.
And the battery's part of electrical and electronics. So would the alternator.
Driver.
Driver. Yes, ma'am?
Braking system?
A what?
The braking system, is that?
Is that big enough to be on its own, or is it part of something else?
It's pretty big.
All right, so we said all together.
It's a big safety system.
Did you say safety?
I said brakes would be a big part of it.
All right, we'll call it safety system.
Traction controls, cruise control, ABS.
And I'll do one more just for grins. And it's part of electrical. What?
Cooling.
I can't hear you.
Headlights.
Headlights will be part of the electrical electronics.
No, cooling. Engine cooling, that kind of stuff's not drivetrain.
Yep.
Safety, isn't it?
No, engine cooling is a requirement of the engine, that's not part of the drivetrain. Engine components.
How about this? Remaining engine compartment. Right? And, all right. Now remember, I said an automobile. You're not thinking outside the box. Literally outside the box. Think about this. I don't know about you. Well, when I buy an automobile, it also comes with that stupid little manual, you know. I was looking at cars this weekend. A manual, I swear, was 2 inches thick for the car.
Jeep, this is.
That's not how you break it down.
All right, documentation, what else then if you're looking at something like that?
Driver. Bill.
Warranty.
Warranty?
Product assurance.
Commercials.
See, what else? When you buy a car, what else typically comes with the car that they don't need?
Insurance.
What?
Headaches.
Headaches, yeah, very good. Okay, so let's see, I could think of, when an automobile is manufactured somewhere and then is shipped either by train or boat or tractor trailer, usually they now cover the vehicle with some sort of plastic, right, so it doesn't get harmed. Do you ever see that? So that's obviously something that's not delivered to you. Well, from that respect, the documentation is. So there's all sorts of other things that are associated with this car system, right? And then there's manufacturing too. And then there's test. So what you have to think about is when you decompose everything, part of the work of systems engineering is to take an extremely huge system and break it down into smaller and smaller and smaller and smaller pieces until it's easy to identify and build that subsystem, and then you build those subsystems together to make your entire big system. So obviously the safety system is everything from analog brakes,
Traction control, stability control.
traction control, all this other stuff. The drivetrain is the engine, the transmission, the differential. For all that matter, we can even include wheels on that and axles. So, but you can break down, let's see, electrical electronics. We have the main computer, right?
Engine ECU.
So that's the engine control unit. But obviously, when you're looking at other electronics, there's anywhere between 30 and 130 computers inside an automobile. Everything from analog braking system to the radio to Windows. So where you identify all of this is part of the work of being a systems engineer, as well as working in a team that designs a system. So when you graduate and work in the real world, you will all work in systems. So you have to look at what's the difference between system engineering, and project management. So some of you will also work in project management. We already know what a system is. System engineering is what we said is a disciplined approach for implementation, integration, operation, definition of a system. And a project manager is a little bit different. The project manager will worry about planning, applying, using funds, in other words, worrying about resources associated with the design of a project. That's why very often when you work in a project, you will have a systems engineer who worries about the technical aspects and the design, and a project manager to make sure that everybody has the resources they need to do the system, to develop the system, to deploy the system. Very often, and this happened to me, I worked as a project manager, I worked as a system engineer, and then I moved into project management because I often saw that systems engineers were promoted to management, project managers were promoted to higher management. So I switched from technical to more or less business, in other words, the dark side of developing a product. Go to the dark side. So why would you want to do systems engineering? Very often a system engineer or a system is pieces built to perform different functions that must coordinate with each other. Unfortunately, sometimes people develop these systems and they don't talk with each other. Hence, why you often have problems. A good example will be there was one Mars flight that crashed into the surface of Mars. A lot of work to get a rocket out of the Earth's atmosphere, from the Earth over to Mars, and in the process of landing, it crashed. You know why? The software, one system was using English units, the other was using SI units. Ooh, didn't see that one coming. So a good systems engineer or system engineering process would have upfront stated everything is going to be SI units and validate that everything works together. Well, you know, this is supposed to be a funny joke that people in the rocket in the space world would really get a kick out of. But every type of engineer sees their own subsystem as being most important. In other words, if you're a communications designer, then you want antennas everywhere and everything else is, you know, just in the way. Or if you're a rocket designer, you're going to put rockets everywhere, and oh, by the way, who cares about the payload that's going to be developed? So, system engineering is built on lessons of the past. In other words, when you are designing a system, you will have lessons learned. In other words, you will identify what went wrong, what did not go wrong. You want to replicate the successes, you want to avoid the failures. A system engineer will record all the successes and failures so it can be used on future projects. I'm just going to go past that one. So, as I showed here earlier, system engineering uses reductionism, which is identify and create a subsystem. You start at the top. Automobile system. And the automobile system includes identifying manufacturing, sales, marketing, transportation, documentation, warranty, financing, manufacturing of the car, and eventually the car. And then the car itself is broken into subsystems. Each one of those subsystems is broken into subsystems. You're building a hierarchy so you can understand how it will work. Oh, by the way, another one up here, even though it's not delivered, we'll be testing. As you're probably aware, there's lots of testing associated with an automobile. What's some examples of testing?
Head-on collision.
All right, collisions.
Mileage.
Mileage.
Top speed.
Say it again?
Top speed.
Top speed.
Emissions.
Say it again?
Emissions.
Emissions. So several of those tests will be required. So that would be an entire subsystem. You have to worry about how you're going to test it. We're going to decompose the life of, these are things that you're identifying. Now you need to identify the processes to develop those things. And part of the decomposing of your project will be to create processes that will help you identify how you go through the different steps. So the big parts of this slide are associated with need. You need to identify that there is a need for this project. There's a need for this product. Then you have to specify or make the requirements for what this automobile will do. Do you have requirements for miles per gallon, head-on crash performance, size, room, emissions, etc.? Then you decompose the problem like this, design each one of the subsystems and components all the way down, integrate them all together, verify, test, operate, and when you're done, dispose of your project. As an example, an aircraft system. You say, I'm going to have an entire system for my aircraft, and this is where I come up with other ideas. Look at that. The vehicle itself is only one of those, whereas there's training. You have to train people how to repair it. You have to train people how to manufacture it. Data, it's kind of like up there with documentation. The industrial facilities for manufacturing, support equipment, et cetera, et cetera, et cetera. In fact, look at that. Systems engineering and program management itself is a completely different area. And then the air vehicle itself. Again, this is a plane. Weapons delivery, survivability, C3I. Somebody told me what that is once and I forget what that is. Command control, Conrad integration. All right, there you go. One of the first aspects of a project is going to be requirements. So let's take a look at requirement analysis, function allocation, and synthesis and design. That step right there. You have seen requirements for our lab exercises, right? How many requirements were there for our little robotic system? Do you remember? Just 4? Wow. I bet you there's a lot more that you could come up with. So part of what system engineering is identifying the requirements in the first place, verifying that that's what you want to do, allocating each one of the requirements to a different subsystem, and then synthesizing and designing everything associated with each of the subsystems so that it builds up a larger system. And then systems analysis, optimization, and control. You have somebody who is always stepping back and taking a look, are these the right requirements? Did you follow the right processes? You'll find out that once you get in industry, there are people, product assurance people, that will look at your work to make sure that the process of work that you're doing is correct. Because very often, for example, governments will require that you do a lot of process validation. So, what I will do right now is ask you to, between you and somebody, you and your lab partner, your assignment now is to write, let's say write with an R. Write the full requirements for Lab 2. Only 4 of them were involved. Did any of them say what the components of the robot are? Did it specify that you had to use a certain amount of voltage for the motors, a certain amount of voltage for the electronics? That you had to use 2 wheels versus 1 wheel? So what I would like you to do right now is to spend a little bit of time, 5 minutes. This one I'm going to want you to actually write down such that I can show it up on the screen. So, write requirements for me. Everything associated with this vehicle. All right, we have some people who are a little bit shy and maybe don't know everything that should go on with this. So hey, just for grins, let's pull open, or let's look at what one of your classmates has done. Let's see, your name's not on it, so I can't embarrass you. Yeah, was that by purpose?
Yeah, possibly.
All right. Must use metal chassis board. Must use 2 wheels with an attached motor. Will use PWM and motor drive. Will use light sensor for feedback. Will use a 3 volt and 6 volt battery pack. Must be configurable, must be programmable. Must go around a 1 meter by 1 meter square 3 times. Must be fully assembled. Must weigh less than a specific weight. The wheels must be in the rear of the robot. Must be able to follow a black line. Okay? So, are those good requirements?
Well, I don't think some of them were requirements. You could easily make the wheels be at the front and just have it go backwards. It wouldn't be very smart, but there's no reason you couldn't do it.
So I guess this is a time that we need to discuss what is the difference between a requirement and a design specification. So what is a requirement typically going to identify?
Weight, size, height.
A constraint, correct?
Constraint, yeah.
So, hey, let's all look at and maybe do a couple of these. What is that? I think it was an eyelash. So requirements for the wheeled robot. First of all, you need to identify the fact that we have subsystems. And you can either write the requirements and then group them into the subsystems, or you can pretty much do it as you go along. So let's identify what are some of our subsystems. We have mechanical, right? We have electrical. And we have computer. So what are some of the mechanical requirements? Well, one of them we know right now is the vehicle shall use the Vigilant robotic platform, which consists of two wheels, a metal platform, and a non-moving, what do we call that? Thingamajig, somebody just said?
Knob.
Knob. For lack of a better word. Here's where it gets interesting. What is the motor? Mechanical or electrical?
It's an energy conversion device.
Which makes an energy conversion device, which makes it what? Electrical or mechanical? So it makes it electromechanical. So for the aspect of this, you're going to have to identify where you group it.
Mechanical.
I declare it to be electrical. The vehicle. Did I spell that right?
Yes.
Shall use a DC motor.
Two DC motors.
With 19-to-1 gearbox. So that makes it kind of sound a little bit electrical, right?
Except for the gearbox.
The vehicle shall use a PMOD H bridge. 2 PMOD H bridges. The vehicle shall use a Renaissance Sakura board. By the way, I said computer, operational. So one of the things we identified was the vehicle shall traverse a 1 meter by 1 meter square. What was another aspect of this?
Must be programmed in C.
Oh, yeah. The Sakura board must be programmed in C. And Arduino C. Why not? Because I can say that. Notice I haven't given numbers for a lot of these others because I may change something a little bit later. What about another operation?
Start and stop at the same point, you didn't do anything, but you didn't put 3 times E there.
What is one thing you notice about all the, here I'm just going to give these numbers. What is the one thing you notice about all of these requirements?
The word shall?
Shall. I don't have very, and the vehicle shall, and it's real sentences, as opposed to being a bullet list. So I'm sure some of you did a bullet list, which will not get you full credit in on an exam, nor will it get you full credit on your job. So you will have to include specifics. I also don't mention in here yet a couple of design characteristics. I don't say you must run the motors at N volts. I could say that. And that's where you actually identify a functional operation specification as a requirement, which is valid. For example, I said that you must use a digital robotic platform. Why? Because I can, right? Because I wanted everybody to use the same exact thing so that we can compare each other for this assignment. If I just said, you are going to create a robotic vehicle that will do this, and then I said, you can do it with anything you want, I would probably get 8 or 9 different things, including, I bet, a Lego Mindstorm, or 2 or 3. I doubt very seriously I would get any all-terrain vehicles, but that's a possibility.
You might have trouble doing a 1 meter square.
Yeah, I might have trouble doing 1 meter square and just run around in a circle. So when you are, also notice that using the systems engineering approach, I have split it into mechanical, electrical, computer, operational. You will need to do the same when we ask you to do an assignment or an exam where it says, here's a robotic vehicle that will swim underwater and grab a unexploded underwater mine. And you're going to have to identify the mechanical, the electrical, computer operational, battery, whatever categories you identify, the subcategories. And it's very likely that I'll have you do something like, I don't know, 15 requirements for a particular system. Hint, hint. Alrighty. So once we have identified our requirements,
Would you put the power source under the electrical?
would you put the power source under electrical? And that's all a matter of what you want to do. I mean, you may put it under power subsystem altogether. And the power subsystem would be battery, safety circuit, charging circuit, all together, versus the electrical or electronic control system. I mean, there's many ways to organize any project, but the whole point is organize it, and then decompose it. So once we have these requirements, you can understand the requirements, how they affect the way in which the entire system must function. What are these requirements? Must traverse in a 1 meter by 1 meter square. Obviously, as somebody said, using extremely large all-terrain vehicle will not work. So, you have to understand the requirement that it's a very small vehicle that might be needed to do this. once you functionally allocate each of the requirements, then that group, the mechanical group, will work on the design of their product or project according to that requirement. If you were to, again, look at the computer operational, the Sakura board must be programmed in C and Arduino C. I immediately know that, well, Sakura is compiled using a web compiler, so it's obvious that you must have internet access. That's going to be part of the design, that when you're developing the system, you must have computer access. That will identify what tools you use. You must use the Sakura compiler. I'm trying to see how this works. I'm just going to go on to this one. This is pretty typical of the US government requirements now for design. And this is an example of the V model of decomposition and integration. You start at the top. You get the requirements and the priorities for all of those requirements. Requirements we already saw for that little robotic vehicle. Oh yeah, develop the system requirements and system architecture, start splitting up all the different pieces to the different subsystems, and then they will write the specifications and identify the plans and how they're going to verify that. Then they design the components, then they fabricate, assemble, code, procure, whatever it is to build up that device. And do you think you just slap everything together and hope it works? All right. You designed it piece by piece, so what do you think you do?
Subsystem trials.
You validate it and build it piece by piece and validate every subsystem that you build, right? Verify the component performance. So if you make a drivetrain, wouldn't it be really nice if you actually tested that drivetrain first before you put it in your final product? If you created a safety system, it would probably be nice if you validated that that brake pump works correctly as you designed it. Then you put all the pieces together to make a larger subsystem. Maybe you do all of the electrical and you validate, oh yes, it runs. And then you add the code, and then you get an entire system. Then you verify it against the system requirements and validate it. So as you go down, you're decomposing to make it smaller. And on the other hand, on the other side of the V, you're going up and you're creating an entire large system out of the subsystems. Obviously, this is as time goes on, you you decompose it and then build it back up. And as you can imagine, as you go along, you get more and more and more accumulated cost. Combined accumulated cost. So a lot of the work done down here is going to cost a lot because there's a lot of people who are building up. But it's always good to do a good job in the early part, because if you make a mistake up there, you got to change a lot of stuff later on. We often use what's called a work breakdown structure to decompose things. This is an example of the shuttle or a rocket. I think this was for Orion they designed this for. May it rest in peace. Everybody know what the Orion rocket was? The Orion rocket was going to be the space vehicle that would go back to the moon, and then Bolton and Obama killed it, and instead we're going to Mars. Bummer. So part of this was the launch vehicle, which had a first stage, an upper stage, and the upper stage engine. In the upper stage, you had all the different pieces. And as usual, people in industry talk in acronyms, so I couldn't even tell you what half of this stuff is. APU, I think, is the analog power unit, but it might be something power unit. Oh well. Auxiliary power unit. I like that one better. Did you look that up?
That's airplanes. They do.
Ah, okay. One way that you can identify also how you're going to how your product is going to work is by what they call a CONOP, or a concept of operation. And you say something like, you will have ignition and liftoff. Then you will separate the upper stage from the lower stage. And then again, you'll separate the upper stage from the lower stage. Then you will have separation of the lunar module versus the command module, etc., etc. That's just an example. I think several of you have done, oops, what happened there? Some of you have done this in senior design, where you look at the different options that you have to design. You'll do a study, a decision factor. For example, you'll say, this is my rocket, I want to have range of a certain amount of distance, and I'm going to give it some weight. For example, the weight will be 2.0 for range, the speed is 1.0, payload. This is just a way to be able to compare different alternatives with some of the major design factors associated with it. Another example will be to compare two different technologies in our field, microcontroller versus a FPGA. This is an example for CubeSat. You know what CubeSat is? Cube satellite. There are many universities that will build a small satellite, which is approximately 1 foot by 1 foot by 1 foot. It is literally a cube. It goes up in a regular spacecraft like a space shuttle or another craft that is going to the International Space Station. They will deploy it, they'll basically kick it out the door, and it'll go on its own, and the hope is that this little cube will transmit and collect data and do their experiments, and it makes a whole bunch of college students happy when it's successful.
That's what it was powered by Android.
It was powered by Android. So here you go, microcontroller versus using an FPGA. So what wins? Oh, look at this. With the weighted average, the microcontroller won. Because the weight they gave on it was radiation tolerance. It looked like, oh, the anti-fuse FPGA did a really good job versus the multi-controller or the microcontroller unit. But in the end, they found it difficult to reprogram in space, and the legacy, it's been used extensively, microcontrollers have been used extensively in the projects.
This might have been really old.
This might not be what?
This might have been really old one.
Oh, a very old one, you think, huh? Said the person in the back who loves FPGAs. We also decompose a design using functional block diagrams. You've already seen examples of that for the robots, right? So I don't need to go into this in much more detail. But very often, when you have very many components, you have to identify one group is going to do part of the design, another group is going to do another part of the design, and when you combine them together, you need to have a common interface between those two parts. So if we look at our automobile system, if we have anti-lock braking system, that's going to have to coordinate with the electrical and electronics. It would probably be very helpful to say, and the ABS system will use the CAN communications bus. So that means, obviously, the electrical and electronics needs to have a CAN bus, which means that the safety system, all the components on here, will need to have individual addresses on the CAN bus and be able to communicate with the CAN bus. And at least you have knowledge of, here are the electrical and here are the programming interfaces that you're going to see between these two subsystems. The same will also be true with mechanical. Each one of these subsystems may have a specific mechanical connection scheme. Locking connectors so they don't shake loose when the automobile shakes down a tough road. And you'll see all sorts of requirements associated with how it interfaces. And the way you do this is to write a document which says, oh, if I have one block communicate with the other block and it has n number of lines, and here you are, there's 1, 2, 3, 4, 5, there are about 12 lines, and this is what this line means, and this is what it's used for. I2C is a communications protocol. So it's used for communicating between two different microcomputers, or microcontrollers. Here's another example. In this case, RS-232 is another communications protocol. You're actually identifying, here's 6 wires, and this is what they mean. Now, anytime you do a decent product, where's my phone again? If I may grab that. You're going to have a budget. Everybody has to work in a budget, right? You can't spend more than what you have. So maybe the designers say, this phone can be no more than 5 ounces. So what does that mean? You actually have to do an estimate of how much that's going to weigh. So you add up, in this case, a mass budget, and you say the LCD is going to be this much, and the case is going to be this much, and the electronics are going to be this much, and then you try and determine what you can pick and choose. The same is going to be associated with energy, power. You could say the same thing over there. The I2C is going to have to consume so many amps, microamps, or milliamps, and the microcontroller is so many microamps, and the safety circuit is so many microamps, and you have to make sure that you're not going to drain your battery so fast because you've decided that the LCD is going to be really high brightness, and it's going to consume so much energy that your battery has to be doubled in size. So here's another example of if we have memory and a processor and relays and I2C, what's the voltage range it runs at, and how much power is it going to consume. And we had a power budget with cell phones to identify, we wanted the battery to last 7 days if no calls came in and you didn't do any talking. So to do that, what has to consume power? How do you go to sleep? How do you shut down certain parts of the entire system? That's all part of the budget. And that's what designers use to decompose your problem. For those of you in mechanical engineering, you probably do this better than I can. Failure mode and effects analysis. You're going to have to find out places where mechanically things will fail. This could also be electrically too. So, what is system engineering? Robust approach for the design, creation, and operation of a system. So you are going to be asked to do and to use systems engineering approaches for the rest of this class. Not just this class today, but the rest of the semester for this. The main aspect of this is decomposition and then integration using the V method. Now there are I threw in here 8 additional rules for prototyping. You can read these on your own, but it's always, I like to start with paper design. It's not a bad thing to sit down and do a design first before you write your software. How many of you actually wrote down and did some paper writing before you started coding? Right? Look at this, the mechanical engineers did it, and the electrical and computers didn't. Oh, shame on you. Especially those of you in embedded systems. I'll get you. Don't forget, you meet the requirements. You don't have to exceed them. Spending additional time will require you to spend more time, or doing additional functionality, you'll do more time. Let's see, and I like this, keys to holding a successful meeting. I just put it in here too because apparently people like to meet, and meet, and meet, and meet. Any questions before we break up?
You're done with us?
I'm done with you.
Donuts and get the hell out.
Thank you very much.